In part three of the discussion, I want to talk about pertinent soil characteristics for dimensions of landscape planning related to urban uses. In talking about this, I want to talk about physical characteristics of soil and how they affect suitability for urban uses. I want to talk about engineering properties, and I want to talk about drainage properties. Pertinent soil characteristics for planning in terms of physical characteristics relate essentially to about 5 different dimensions. One is soil particle size. What is the size of the particles that actually make up soil? Secondly is soil texture. How are those particles agglomerated into components? Third is the structure of the texture of the soil. Fourthly is level of compaction, and finally is depth to bedrock. In terms of talking about mineral particle size classification, when we're talking about soils, we normally talk about 3 different particle sizes. On the one hand, we can have sand particles that range in diameter from 0.05 millimeters to about 2 millimeters. We can have silt, which are smaller, from 0.05 millimeters down to 0.002 millimeters. And then essentially microscopic particles associated with clay that are less than 0.002 millimeters in size. We often, with respect to sand, talk also about gravel because oftentimes, especially in Minnesota, we find gravel mixed in with clay, silt, and sand particles. So in addition to talking about particle size, how large are the mineral particles that make up the soil, we also can talk about the particle shape. What is the shape of the particle of sand? Is the shape angular or rounded? Angular meaning it was not worked by water, and rounded meaning, generally speaking, that it has been under the influence of water as it's been dragged through the landscape. We often use the soil texture triangle as a means of characterizing particle sizes. The soil texture triangle involves 3 different metrics. First of all, it's the percent of soil particle size that falls into the clay definition from 0 to 100%. Secondly, it's the percent of particle size that falls into the silt designation, again from 0 to 100%. And thirdly, it's the percent of the particles that fall into the sand classification, above 0.05 millimeters. For any given soil sample, then, we can characterize what percentage of the soil sample contains clay from 0 to 100, what percent of the soil sample contains silt from 0 to 100, and what percent of the soil sample contains sand. And we can talk, for example, about a soil that has 35% clay. It's approximately 1/3 of the way up the percent clay axis, about 35% silt, about 1/3 of the way down the percent silt axis, and about 30% sand, again about 1/3 of the way across the percent sand index. This then we characterize as a clay loam. It contains roughly 35% clay, 35% silt, and 30% sand. There is a term that's often used in describing soil texture called loam. Loam inherently means that the soil contains all 3 of these different particle sizes. And depending upon how much the relative composition of each of these particle sizes, we can have sandy loam, as we see in the lower left-hand corner, which has a higher percentage of sand than it does of either clay or silt. Or we can talk about silty loam, which has a higher percentage of silt. Or we can talk about clay loam, which has a higher percentage of clay. So soil texture then helps us characterize and understand what the mix of particles is by particle size. Once we have characterized particle size, then we can also talk about soil structure. Soil structure refers to the clumping together of the mineral particles into aggregates that are often referred to as PEDs. PEDs, the structure of the soil then affects water and air movement, biological activity, and root and seedling growth through the interstitial pore spaces between the soil PEDs. So in the lower left-hand diagram, we can see the soil particles, the PEDs themselves, that are agglomerated into these clumps of the kind of brownish red color. And in between the PEDs, we can see water and air space. This is pore space that exists in between the soil PEDs themselves. It is through these interstitial spaces between the PEDs that water moves through the soil. And oftentimes it is through these interstitial spaces between the PEDs that plant roots penetrate the soil. Different types of structure have different volume of airspace. They have different ability of water to flow through the soil, and they have different ability of plant roots to penetrate the soil. We can talk about a granular soil structure, a blocky soil structure, a prismatic soil structure, columnar, clady, and single grain. Single grain is essentially the same as free sand. So soil structure, as I said then, affects the volume of airspace in the soil. When the soil is crushed, for example, then the airspace in the soil is destroyed. Going back to this diagram, the blue essentially goes away, and there is no airspace between the soil particles because it's essentially been crushed. And as a result, air cannot circulate through the soil, nor can water, and it becomes more difficult for plant roots to penetrate the structure. So it affects the volume. Soil structure affects the volume of airspace in the soil, the ability of water to flow through the soil, and the ability of plant roots to penetrate the soil. We see here pictures of 4 different types of soil structure. In the upper left, we see a granular structure, a blocky structure on the right, kind of sort of a prismatic, a rectilinear block. In the lower left, we see a prismatic soil structure and then a platy soil structure on the lower right, basically a series of horizontal plates within the soil itself. Importance of protecting soil structure is that without soil structure, there's no air in the soil. With no air in the soil, roots receive no oxygen, which they need, and there is no capacity or a very greatly reduced capacity of water to be able to move through the soil, to enter and move through the soil. So the trick then is, how do we actually use the soil without creating soil compaction? How do we prevent soil compaction? One of them has to do with preventing capping of the soil, that is, placing an inordinate amount of weight on the surface of the soil that essentially crushes the soil. And the first thing that is destroyed when the soil is crushed is the pore space that makes up soil structure. As soil structure is destroyed, then plant roots have a much more, greater difficulty in penetrating the soil. In terms of preventing soil structure in the agricultural landscape, it involves different kinds of what are called minimum tillage practices, wherein the tillage that's done to open fields for planting is done in such a manner so as not to crush structure, to maintain good soil structure, allowing water, air, and plant roots to penetrate into the soil. We see in the lower right-hand corner a process called aeration, where the soil is penetrated to open up airspace, and over time then the roots move into the created airspace, and we rejuvenate soil structure through the process of aeration. In the upper left, we can see the influence of decreased soil structure associated with moisture conditions within the soil. A very wet soil, as we see on the right-hand side of the upper right diagram, pressure of tires or vehicles going across the surface of the soil penetrates much more deeply into the soil horizon than is true in dry conditions. Oftentimes in an urban context, in a construction context, we can actually insert grid structures into the soil, onto the surface of the soil, to help retain good soil structure. And here we see a couple of different examples. On the one hand, where we're creating a urban play space and using a structure to help retain structure underneath of the board structure here, and retain the structure of the soil beneath the surface that's going to be created. On the upper right, we see a hexagonal grid structure that is placed onto the surface of the soil. The idea is to let the hexagonal grid structure support whatever pressure is placed on the soil, rather than the soil particles or the PEDs themselves. You see another type of structural device in the lower right and the lower left. These structural devices are designed to support heavy weight on the soil, prevent soil structure from being compacted. Here we see a driveway that's actually looks as though it's a yard, but in fact it's got a structural component to it underneath the surface, whereby the structure of this 1954 blue Chevy convertible is supported not by the soil itself, but by an underlying structure into which the grass that you see growing has been planted. So the structure of the vehicle is borne by the underlying grid structure. The weight of the vehicle is borne by the underlying grid structure, and the soil structure is protected. Depth to bedrock is critical because it determines the depth of growing media. It also affects drainage properties, and it affects construction feasibility. Where we have shallow soils, as we see at the top of these dolomite pinnacles, which are underground bedrock pinnacles, we have very little room for drainage properties. It's more difficult to construct because the depth to bedrock is quite shallow. Whereas in the areas where depth to bedrock is deeper, we have a lot more latitude in terms of construction feasibility. We have a lot more depth of growing media and drainage properties. We have a lot more soil in which to support drainage of water into the soil and through the soil.